Hello, I'm Sophie Rovner from the American Chemical Society. Welcome to this media briefing from ACS Fall 2022. Wooden objects are usually made by sawing, carving, bending, or pressing, but that is so old school. Now, scientists are reporting at the ACS meeting that flat wooden shapes extruded by a 3D printer can be programmed to self-morph into complex 3D shapes. In the future, this technique could be used to make furniture or other wooden products that could be shipped flat to a destination and then dried to form the desired final shape. To give us more insight on this work, we're joined by Dr. Eran Sharon and Ron Kam from the Hebrew University of Jerusalem. Thank you for joining us today.
Thank you for inviting us.
Pleasure to be here.
First, I'd like to ask what problem you were trying to solve with this research.
Maybe I will start. So this work is can be viewed in the broad context of this field known these days as self-morphing. And we can best understand it by looking around us, everyone who is viewing this right now. We see many objects, and even the room we're sitting in. These are all solid structures that were designed to have a specific shape, a three-dimensional shape. And if you think about the techniques that are used by humanity, these are very, you could say, even violent techniques. You take a material, you treat it as completely passive, you press it, you bend it, you carve it, you machine it in order to get the desired shape. If you look at nature, nothing is made this way. Tissue expands gently and the shape emerges out of this distribution of different expansions and shrinkages. And this is self-morphing. In the last decade plus, we started learning how to make self-morphing synthetic artificial structures. In general, when you treat the material as a partner in the design, not as a passive entity which completely obeys your external input. You could save energy, you could save effort, you could save a lot of waste and reduce your environmental footprint. Now, until recently, all self-morphing objects were done with synthetic materials that are not very environmentally friendly. And I think what Doron managed to do to combine the technique of 3D printing where you can place your desired piece of material in the right place, in the right orientation, and do it with wood, and even with wood which is obtained from wood waste. This brings this self-morphing to its best in terms of material itself is very environmentally friendly. The fact that you can ship and store flat things saves a lot of transportation, energy, etc. The fact that the shape itself emerges and you don't need to invest so much energy in making it, all of these aspects combine to a very novel and environmental friendly structures.
So how did you investigate this?
Okay. So recently we have created a wooded ink for a 3D printer that is composed of 100% wood-based material without any addition of synthetic resin. And the idea came just from looking at the plant cell wall. We identified two main groups of materials, cellulose and hemicellulose, that are the, let's say, the natural binders in the plant cell wall. And in our case, this is the binders for wood waste particles. So we started to 3D print this wooden ink, and we saw that just like native wood, in some configuration, our printed objects were warped. And in nature, if you cut a tree, chop down a tree, the tree starts drying, and what it means is that water evaporates from the wood. So as water evaporates from the wood, it loses volume and shrink. But because constraints of the plant cell orientation, it warps. And in our case, the 3D printed object warps too, but the constraints now are the 3D printing parameters. So in our extrusion-based 3D printing, we have an extruder that can extrude wooden ink on an XY plane. And we control the extruder pathway where the extruder will move, and control what will be the flow rate of the ink. So how much material should we deposit? So we've printed rectangular object with different printing parameters and let the object to dry and warped. And at the end, we looked at the influence of the pre-designed pathway and the ink flow on the final dried warped object.
And how do you control the final shape of the objects?
So specifically, we have two knobs. One is a direction and one is a printing speed. So the direction is the pathway of the nozzle, how the extruder will move in space. And the printing speed is the flow rate of the ink. So if you want each time to result in a constant printed cross section, height and width of extruding material, for slow velocity, you will need to extrude the material slowly. But if you're printing fast, you will need to extrude the ink fast. So at the end, we printed the same amount of the material in the same initial dimensions, but got different warped objects. And we saw that there is a dependency between these two knobs, flow rate and pathway, on the final warped object. And if I need to go in more details, as we increased the flow rate, we aligned the ink particles more. And by that, we can control the intensity of the warping just by adjusting the printing speed.
What sort of shapes have you developed?
So since this research was kind of a first step, we as scientists, so the work was done like a collaboration between a physics group, my group, and a group in the chemistry department of Shlomo Makdassi, where Doron is a PhD. So the idea was to see that we can create basic structures in a controllable way. Now, the theory of differential geometry, the geometry of curved surfaces, tells us that each surface is a combination of, and we can imagine it, that it is a combination of dome-like shapes, which can be flipped into a bowl-like shape, it doesn't matter, saddle-like shapes, and things that are twisted. So we basically tested our capability to produce such basic elements that compound every general shape, and not just to make them, but to do them in a controllable way, where the helical pitch, for example, is predictable, where the saddle shape, again, is predictable. And the important step here was to map the properties of this specific system of the printed wood into the theory of what we call the theory of incompatible elastic sheets. It's a theoretical framework that allows prediction for self-morph structure. It was developed at the Hebrew University, and it can handle many different systems. The important thing was to map quantitatively the properties of this wooden printed wood system into the theory. And this was a very fruitful collaboration that Ido, as a physics student, and Doron, as a chemist, did together.
So in closing, how might people be able to use printed wood in their everyday lives?
Okay, so imagine a council that performs pruning and cleaning of public spaces, chopping down branches or picking up leaves. And this is already happening nowadays, but now this garbage can be converted maybe to this wooden ink. So there is no need for transportation of ink from manufacturing companies. The material is near your house. And then students, kids, residents, makers can take this ink and rebuild, not repair, rebuild their broken chairs or tables. And because we take the advantage in the warping, we can print very fast and let the wood just be wood, and by drying and warping to our specific design. So we print fast, easy structures and let the warping deal with complex designs.
All right. Thank you, Haran and Doron, for sharing your research with us.
Thank you.
Thank you.
Be sure to check out our other media briefings for ACS Fall 2022, which will be posted throughout the meeting at www.acs.org/ACS Fall 2022 briefings.